in this class we are going to talk about design of digital voltage mode control using frequency domain approach. So, we will first recapitulate our frequency domain design of analog voltage mode control. Then we want to design digital voltage mode control using a frequency domain approach in a buck converter, and this is using an indirect method. Then we will also design digital voltage mode control in a boost converter using frequency domain approach, and finally I want to show some design case studies and MATLAB simulation. So, if we consider the buck converter voltage mode control, this is the analog voltage mode control which we have discussed multiple times. So, what are the primary loop shaping objectives? So, if you take the small signal block diagram, that this small signal block diagram, this is our control to output transfer function, this is our controller or compensator, this is the modulator gain, and we know that Fm is equal to 1 by Vm, where Vm is the peak voltage of the sawtooth waveform, and this is the open loop output impedance, and this is the audio susceptibility. So, and we want to shape the loop transfer function in such a way we can meet the desired crossover frequency as well as the phase margin. So, if we write the loop transfer function expression, so this term is associated with, this is nothing but our GVD, this is our modulator gain, and this is the controller that we have to design. So, for the planned transfer function, the GVD, the ESR 0 we know, all this the omega 0 which is the undamped natural frequency, then the Q factor as well as the characteristic impedance, all these expressions for the open loop practical synchronous buck converter that we have discussed in lecture 30 in our earlier NPTEL course, which link is given here. Now, our first objective in the, we want to design a PID controller, and if we take a practical PID controller, we know this is the proportional part, this is the integral term, and this is the band limited derivative where we have a derivative filter which is a low pass filter, and this is the derivative gain, this is the derivative gain. Then if we write the polynomial, then we can take Ki out, and these are the expression which is coming out from this left side, and where K1 can be, and we are talking about the design of voltage mode control in a buck converter, where we are going to design using the conventional stable pole 0 cancellation, where K1, if we take K1 equal to 1 by Q omega 0 and K2 equal to 1 by omega 0 square, and tau d which is nothing but RC into C, that is the ESR, the time constant due to the ESR of the capacitor, then the Ki, which after this pole 0 cancellation compensation, we will get that this Ki term will be omega C alpha Vm by Vn, and we need to select the crossover frequency, and the then we can find out the integral controller gain. So, in this controller we have one unknown variable, 2, 3 and 4 tau d, where we have one equation by means of pole 0 cancellation, 1 will get, 2 will get from here, 3 will get from here, and these things are coming from our pole 0 after pole 0 compensation, and the detailed steps we have again summarized in the previous lecture in this course in lecture number 42, just previous lecture. We are just taking that Ki expression which we have already derived in the previous lecture. Now, K1 and K2 in this expression, because we got the PID controller expression which in terms of numerator and denominator polynomial, where K1 equal to, in term, it is a function of Kp, Ki and tau d, Kd. So, these things are written. Now, we want to, under voltage mode control, now we are talking about digital voltage mode control, and we have discussed in, I think in lecture number 40, that we have shown that if we incorporate that delay, that means e to the power minus tau d, and this delay is due to our ADC conversion time, that is our ADC plus our dPWM delay which is d into t, where d is a duty ratio, and that we have discussed in lecture number 40. We have shown that in lecture number 40 that if we incorporate this delay into small signal transfer function, then this small signal transfer function up to 1/10 of the switching frequency perfectly matches with the discrete time small signal transfer function, which have been derived based on the exact, I will say, taking into account all the delay, the discrete time model. But we have shown if we derive the small signal transfer function using continuous time approach, and if we incorporate this delay, and then if we derive the discrete time small signal model, they match reasonably accurate, almost accurate, up to the 1/10 of the switching frequency, which is our desired control bandwidth. Now, if we consider the analog voltage mode control loop transfer function, then if we incorporate this delay, then we can approximately get the loop transfer function under digital voltage mode control, and we have shown that this delay amount is this. Next, this was the loop transfer function of the analog voltage mode control, and we are just taking the delay term, and it can be shown, it is well known that if you take e to the power minus s tau d, this term, and if you obtain the frequency response, that means if you write s equal to j omega, then e to the power minus j omega tau d, this term magnitude is 1. So, that means the delay will not affect the gain plot. So, the gain plot remain unaltered, it will be the same as the analog control gain plot, but the delay will have a phase, because if we take e to the power minus j omega t tau d, you will get simply minus, that means minus omega tau d. So, it will give a linear phase characteristics, where the phase will proportionally vary with the frequency and the tau d will come into picture, and this can substantially reduce the phase margin compared to the analog control. So, now that means we got the loop transfer function with the of the digital voltage mode control with delay, and this is the, if we write in terms of polar form, so this is the magnitude expression and this is the phase expression. What is the magnitude expression? So, first of all, the phase expression will be same as the phase expression of the analog controller, which we have discussed in lecture number 42 in this course, that we have discussed in the previous lecture. In addition to that, we will get another phase lag, which is minus omega tau d, and r omega, which is same as the earlier, which is k I v in by alpha Vm omega, and this omega, now alpha equal to r equivalent. So, this is the r equivalent, Re, or you can say Re. In fact, this is the Re, that expression was there. Now, at gain crossover frequency, this magnitude will be 1, because we are talking about the loop transfer function frequency response, which will become 1 magnitude at gain crossover frequency, and this is the phase expression. Now, how to design at gain crossover frequency? We know that r this omega c, that means if we write omega equal to omega c, it will be 1. So, from this expression we can get the integral gain in terms of alpha, which is known. So, alpha is our r plus Re by r. It is known because Re is the equivalent resistance, which is coming, is a sum of the DC resistance of the inductor plus the RDS on, and Vm is the peak voltage of the sawtooth waveform, omega c is the crossover frequency, and Vin is the input voltage. Now, the phase margin, if we take digital voltage mode control, it is simply because we are talking about the PID controller and we are trying to obtain a first order integral term. In analog control, we are trying to obtain the expression of the loop transfer function simply gain by S. That means, in case of analog loop transfer function, we are trying to obtain some gain KL by S, that is our desired objective, by means of stable pole zero cancellation. So, in case of analog, our phase of this, if we take loop transfer function j omega, this phase will be simply minus 90 degree, because it is just 1 by S. And if we write the expression of phase margin, it will be 180 degree minus of 90, so 90. But because of the delay, you are getting an additional term, so that will actually try to reduce the phase margin compared to analog control. So, now the question is, if we compute, let us say, at, suppose if, now it depends on the delay. So, if we take the crossover frequency 1/10 of the switching frequency, which typically we take, and if we take the delay as a fraction of time period, that means we can take delay maybe 1/10 of the time period, or it depends. So, if it is written k times t, now then it can be shown that omega c tau d, because omega c is this, if you substitute, then you will get the delay contribution due to that phase contribution due to the delay is k times 36 degree. That means, if k equal to 0.1, that means if it is 1/10 of the time period, then it will contribute to 3.6 degree additional phase lag. And if the delay now slowly go towards the time period, because we have discussed in the earlier architecture, that means it can be possible that delay can be a complete switching cycle. In that case, k will be 1 and you will get an additional phase lag of 36 degree. So, that you have to take into account in the design process. Now, once we design all the parameter, because we know the ki value, we have obtained the other parameter of the PID controller. So, if we summarize, first thing we know k1, k2, which is a function of kp, ki, kd, and we know k1 by means of stable pole 0 cancellation, it is 1 by q omega 0, and we know the denominator polynomial of the buck converter. What is there? If you take GVD, you will get some gain into ESR0 divided by, you will get 1 plus S q omega 0 plus S square by omega 0 square. So, I am talking about this q omega 0 expression by means of stable pole 0 cancellation. Then we know the expression of omega 0 and q. We also found the ki from the loop transfer function at gain crossover frequency. Now, we have to map by means of backward difference formula. So, we know ki and we know k1, k2 and tau d. We also know how they are, this k1, k2 is a function of the power stage parameter, and then we want to calculate kp from k1. That expression also we have shown, which will be kp equal to ki k1 minus tau d, and since everything is known here, so we can get kp. Next, kd, again by solving k1, k2 we can get kd, and this is also a function of ki and all. So, since we have already found here, we can find kd. Once we get integral gain in analog domain, proportional and the derivative gain, these are all in analog domain, then it is a matter of conversion, like how do you convert that analog gain into digital gain, and there we are using a backward difference formula, and it can be shown the proportional gain will remain same. Integral gain of the discrete domain will be simply the analog integral gain into the sampling time, in this case which is nothing but the switching time period. And for derivative gain in digital domain will be derivative gain in analog domain divided by Ts. Okay. So, by that way we can design the converter and we can actually design a compensator. Now, if we go to a MATLAB case study, so I am showing a buck converter case study, and here again we have the power stage parameters, and we are talking about the R1 is the initial load resistance is 1, and we have considered the delay due to ADC conversion is T by 10, and then all these thing actually we have discussed in lecture number I think 35 and 36, where we have validated the model. Now, here we have total delay, that Ts plus Dt, that is the dPWM delay plus the ADC delay, and we have discussed in our earlier NPTEL course that how to design a voltage mode controller using stable pole 0 cancellation. So, we are following the same method. The only difference, in case of the regular continuous time transfer function, we will get GVD, which is the control to output transfer function, as an expression of V in alpha ESR. I think that we have discussed the whole expression in lecture number 42. Now, we have a delayed version of this transfer function. That means, if we go back to our loop transfer function, in digital control we have an additional delay, and that delay is E into T total. That means, the total delay, which is a conversion time, that is tau d conversion time plus our dt, that is a dPWM delay. Now, we want to design a controller. So, the first thing we are designing a controller, we have discussed just now the K1, K2 by means of exact pole 0 cancellation, and then we can get omega c. Suppose if we set the crossover frequency 1/10 of the switching frequency, then we can compute the analog integral gain. We have just now shown the tau d is the derivative filter time constant, then the analog proportional controller, then the analog derivative controller, then we can get the analog transfer function GC. Now once we have, then we can draw the loop transfer function of the analog and the loop transfer function of the digital, which is nothing but the analog loop transfer function multiplied by the delay term, and then we can get the Bode plot. We can compare to see how much phase margin is affected because of the delay that we want to see at our gain crossover frequency. And finally, we want to convert all these gain into digital discrete time proportional controller, discrete time integral controller and the discrete time derivative controller. And here we are running the simulation for 2 millisecond, we are applying a step transient at 1 millisecond and we are applying a load step of 20 ampere. And if you go to our Simulink diagram, okay, so Simulink diagram, so I want to show that this is a Simulink block diagram and here we are applying, actually this diagram we are applying a load step transient. Sorry, this is the boost one. Actually I want to go here. Okay, yes. So here I want to show, this is the diagram. Here we are applying a load step of 20 ampere here, I0 step at T step time where we have applied the load. This is the digital voltage mode controller and we have explained this why these delays are incorporated in lecture number 35 and 36. We have discussed in detail, and this is our PID, discrete time PID controller. This is the KP, this is the discrete time integral part and this is a discrete time derivative part that we have discussed. Now we want to run a case study for a load step transient which is designed based on our traditional analog control, and we want to check what happened. Okay. So before we move, first I want to show the Bode plot. So let us go and I want to change some setting, that means we have to hard limit, we have to limit up to half of the switching up to the switching frequency you are limiting and phase also you are wrapping. Okay. Now I want to show that our all, okay. So here we want to achieve a desired crossover frequency of what? We want to achieve desired crossover frequency 1/10 of the switching frequency. So switching frequency is 500 kilohertz and 1/10 of this is a 50 kilohertz, which is the case. So if we limit this to 1, yes, so this is what I am showing. So here is our 1/10 of the switching frequency, and you can see there is an additional phase lag due to, because we know for exact pole zero cancellation in analog control the phase margin was always 90 degree, but now if we take the phase here for the digital, you are actually getting a phase. So if you write it here, if I zoom this part, I want to show that you are losing some phase here, and that may not be significant because we are losing around how much, it may be some 20 degree or so. Okay. And based on this phase margin criteria, I mean whatever we have discussed, we are actually designing this controller, and this is the response of the load transient response. And we know earlier we also have discussed that in case of load transient, if we simply shape the loop transfer function, it is not enough because we have to shape the closed loop output impedance, and that means since the loop transfer function does not include the open loop output impedance, so that is why this method may not be a good solution in terms of load transient response. Now we want to go next, that means we want to consider the alternative approach. In the alternative approach, we have discussed the same loop transfer function, everything remains same, the same PID controller, but we want to visualize the derivative gain as the, it is, if you take the derivative of a buck converter, let us say if you ignore the effect of ESR, it carries the information of the inductor current and the load current, because it is the capacitor current. C dVdt is equal to IC, which is a capacitor current, and it is IL minus I0, which means it gives indirect information of the inductor current and the load feed forward. So here we can take KD equal to C directly, but it may be large and it may inject some noise. So we are setting the derivative gain just 0.1 times of the output capacitor, and tau d you can set to t by 10, t by 20, t by 2. So, it is not a big it's not a problem. Then how do you design? So, in this case we are first setting again the proportional control. We have taken k d equal to this, tau d equal to this, and we have taken the integral gain same as which we have discussed earlier, because we just want to take integral gain to start with, that is the 1/10 of the switching frequency, and Vm is the peak value of the sawtooth waveform. Now, in this controller we have 4 unknown Kp, Ki, Kd and tau d. Here we already set 3 that means 3 parameter Kd, tau d and Ki. So, 3 parameters are already set. Now, the fourth variable which is the Kp, that we have to select in such a way we can get the crossover frequency close to 1/10 of the switching frequency. So, where it is very difficult to analytically compute the expression of Kp, but you can always check by means of Bode plot that what should be the value of Kp, so that you can get the crossover frequency nearly 1/10 of the switching frequency. So, we will summarize and we will take the case study again. Okay, so that means again if we design, so maybe we can go and check the case study. So, in this case now we are designing the controller using the alternative way, that means we are commenting this, and this is the alternative design approach that I have discussed. So, in this approach we have set Ki analog controller gain, integral gain, that I have just discussed, Kd equal to this, tau d you can take t by 10, t by 2, does not matter, and then we are taking the proportional gain to be 5, and we have to check that how much crossover frequency you are achieving, and then we want to run and verify. So, let us do that. Now, we are running this and we want to check first our, so we want to check, that means we want to use hertz, and here also we want to limit 6, 0.5, 0.5, okay, and we want to check all the phase characteristic. That means here it is like this is 10 kilohertz, 20, 30, 40, 50. So, it is roughly around 50, that means it is 51.5. So, nearly 1/10 of the switching frequency, that means we have set the gain to achieve. Now, in case of analog control, which is the blue line, you see the phase margin is 63.1 degree, whereas the digital control it is 56. That means there is a just around 8 to 10 degree phase shift. That means it is 63 and this is let us say 56. So, around 7 degree phase degradation. Okay, phase margin is degraded by 7 degree. So, it is not a big deal because it is much higher than 45 degree. So, it should be okay. Now, we want to check, here we are not doing any exact pole 0 cancellation, but another interesting point, you see the gain plot of the analog and digital, they are exactly identical, because I told you the delay will have no contribution in the gain because its magnitude is 1, but it will contribute to the phase, and the phase will deviate drastically as we move further and further, because it is omega into tau d. As omega increases, the phase lag also increases. But interestingly, if you check the load transient response in the output voltage, it is much better than the earlier solution. But that means we are still using 1/10 of the switching frequency, we are achieving there as per the exact cancellation, our loop transfer function shows close to more than 80 degree phase margin, and with 1/10 of the switching frequency. Here our phase margin is around 50 degree or plus 1/10 of the switching frequency, but the transient response is much better in terms of undershoot overshoot. Now, we want to compare this design with the earlier design. So, let us go and compare. That means we have method 1, this is the alternative method, and we want to continue with the earlier method. So, here we want to comment this line, comment, and we want to discuss this alternative method, and we want to use a different color. That means the Bode plot also dotted, all the dotted, and if we dotted, and we want to discuss, plot here also we want to use dotted. So, all dotted dash line will be 1, which is for the second design. So, let us run the simulation and we want to compare. Now, I want to show, before going to the transient response is the phase plot. Okay, so I want to show you can see that if we go by the traditional pole zero cancellation, the analog control we are getting 90° phase margin, and which actually because of the exact cancellation, and that is practically impossible. But if we incorporate digital delay, then we are losing a phase, and this phase is around 7° we are losing, so 83.4, but the gain crossover frequency is 50 kilohertz, which is, and the other design we got slightly higher and the phase margin is much lower. And you can see, since we are not doing any exact cancellation, so there can be a LC pole effect, that means the phase, you can say there is a phase swing, and also amplitude has a peaking effect. Now we want to compare what is our transient response. So we want to see the transient response, and if you compare the transient response, that you can see that the dashed line is coming from the exact cancellation, and that is much poor because it has more like a overshoot, undershoot, as well as the settling time is also longer, whereas the alternative design approach is far better and it can settle much faster. And if you take the inductor current waveform, there also you can see not drastically different. Yeah, so in summary, we want to discuss that this alternative approach is much better because we are visualizing this controller as if the derivative controller is carrying the current and the load information, and that makes the whole design perspective different. Now again, for the same design, if we get Kp, Ki, Kd in analog, then we know just we have to convert into digital by means of backward difference formula, and that we have already discussed. Now we are talking about a boost converter, voltage mode control. So this is the analog voltage mode control of a boost converter, and now this is the loop transfer function of the boost converter. Here we are talking about an ideal boost converter, and this particular expression shows the boost converter GBD, which is the control to output transfer function. Again, this is the modulator gain and this is the controller. Now we want to design a PID controller for a boost converter, and we know that in a boost converter the exact stable pole zero cancellation that we have discussed in lecture number 42, these are the parameters, and these parameters are function of Kp, Ki, tau d, and we can obtain Kp, Ki, d. Now if we do go by exact pole zero cancellation, stable pole zero, we know in the boost converter we will get a loop transfer function like this. There will be some gain, then 1 by S term, and then we are placing the controller pole in coincidence with the RHP0 of the control to output transfer function. Then we also know the traditional way of finding the loop frequency response of the loop transfer function, and this expression we already know, and this we have discussed in lecture number 42 in this course as well as 36 in the earlier NPTEL course. Now if we take a digital voltage mode control, again we are incorporating just a delay, and we are continuing with the same continuous time small signal model, and again we can show that this gain plot will not be affected, but the phase will be affected because of this delay. And then if we want to design based on the gain crossover frequency criteria, so we need to set the gain crossover frequency. Since it is a voltage mode control, so typically it is better to use 1/5 of the RHP0, it should be smaller, and we know that we have discussed in lecture 36 in our earlier NPTEL course. So we set the gain crossover frequency 1/5 of the RHP0, then you can compute the phase margin, and this phase margin computation we know from the analog control voltage mode control in case of boost converter, but because of the digital control the additional term will come due to the delay, which is a linear phase. Then for given tau d, because we have to find how much propagation, how much is the delay is there in the digital control, that means this tau d, again what is this tau d? It is the ADC conversion time plus the dPWM delay, and dPWM delay is nothing but d into t, and this whatever you take, that means the conversion time. Now for given tau d, you have to check whether by means of this analytical computation can you meet more than 45° phase margin. If it is not, then you may have to reduce this factor, so that your crossover frequency you have to reduce further. so that it will impose a constraint in the gain crossover frequency, which is nothing but the closed loop bandwidth. Now, if one, that means if the step 3 is not satisfied, then we have to go to step 1, reduce Kp and repeat the same process till we meet the required phase margin criteria. Once it is done, then you are set with the phase margin. That means you can obtain what is my gain crossover frequency, that will be known from this expression. Then you can find out Ki by this formula. That means the integral gain is known. So only integral gain was unknown, other proportional derivative everything was known from exact pole 0 stable pole 0 cancellation. So again we can convert, that means if we summarize K1, K2, K3 and tau d here is the RHP0, K1, Ki we just now we got, Kp can be written in terms of K1 tau d, Kd can be written, so because if you take this expression and it is actually coming from a practical PID controller, then we can convert this gain into discrete time. So we want to show MATLAB design case study using stable pole 0 cancellation, and for buck converter we have already have shown, that means the case study. These are the design summary. For the boost converter, we may not want to go by this method, we can go it, but we want to go by the alternative method. That means the alternative method says that for the buck converter, we have to set Kd equal to 0.1 times C, tau d T by 10 and Ki is this. Then we have to select Kp in such a way, that means our phase margin should be more than 45 degree. And we know that GVD, that means the loop transfer function, right, which is for the analog digital control, it is nothing but the loop transfer function of the analog control into e to the power minus s tau d. So for including this delay, we have to set Kp in such a way, the loop transfer function, if you take the loop this j omega, this one, so the phase margin of this should be, that means what is the phase, that if you compute the phase margin, it should be greater than 45 degree. Okay. So then for the boost converter, we have to take Ki, because we have discussed the Ki. If you go back to Ki in the boost converter, Ki was coming to this, and we know what is omega c for a boost converter. Typically it is RHP0 by 5 or even less. That means if we want to consider the worst case, we have to take the worst case RHP0, and omega c we are taking like a 1/10 of the RHP0. That means for the integral gain selection, that means we have selected here, in this case this particular expression is nothing but omega c worst case, that means the worst case divided by 10, omega c worst case, which is nothing but omega c worst case, which is nothing but we are talking about the RHP0 worst divided by 10, just to be in the safe side, and that means it is 2 pi, and that is the expression, and this expression we already have from the boost converter design. So that means Ki we know, Kd as is said, we can set just simply 0.1 times C, tau d T by 10. Now we have to play with Kp such that we can meet certain phase margin, including the delay due to the digital controller. So let us go to the case study of this boost converter. Here we are talking about, now if you go to the other folder, so this is the boost converter case study. Now we are going to design this boost converter, whatever I have discussed, the GVD, all these transfer functions are derived. Here we are designing Ki, that is the integral gain in analog domain, I have just discussed. What is my RHP worst case? So the RHP0 worst case will coming from, that means we know that it is, what is the RHP0 worst case? So let us go back and take, what is my RHP expression? It is R1 minus d whole square by L. If you want to write in terms of load current, so R is nothing but V0, which is, if we maintain the output voltage to Vref by means of integral, it is Vref by simply I0, Vref by I0, that is our R. That means for worst case, that means R has to be minimum, which is nothing but Vref divided by I0 max. That means we can write this one is nothing but Vref by Li0 into 1 minus d whole square. So, what is my RHP0 worst case? So, it will be Vref 1 minus d whole square L I0 minimum. That is the expression of the RHP0, and that I have shown here in this code. That means Vref I0 max 1 by L. Okay. So, there should be 1 by d square. Yeah, fine. Now, we are designing. So, this case Kd we have set 0.1 times C and tau d. So, I have set the proportional controller gain, analog gain is just 1, very small gain, and let us check how does it look like. That means, and this is the voltage mode controller of the boost converter, and if you go inside, again we are using a PID controller, and finally you have to get the digital PID controller gain, and whatever you obtain again we will convert into analog to digital conversion, and that will be plugging in into a Simulink model. So, let us run it and see what happened. So, in this case we are now running a boost converter. So, let us first consider the case study. First change the time unit to hertz. We want to limit to 0.5 E6, that is the switching frequency, and we want to also wrap the phase. And now let us come back. We want to see all the stability margin. Now you see the gain crossover frequency is coming to be slightly above. That means if we take here, the gain crossover frequency is coming to be how much? Around 12.2 kilohertz, whereas the switching frequency is 5 kilohertz, because we are talking about the worst case load current, which is a 20 ampere load step. Okay. So, at 20 ampere, which is the maximum, sorry, I have to check, not 20, what is my in the MATLAB, we have to check what is the worst case. Yeah, so worst case we have taken 5 ampere. That means Vref is 5. So, 25 square. So, that means 5 into 5. So, we are talking about 25 watt. You can always increase that, no issue, but I have taken 5 ampere is the maximum load current, and that is why we are getting 12.2 is the crossover frequency. But here the phase margin we are getting around 21.5, which is not very high. So, you need to really decrease the I would say this this gain in order to achieve 45 degree phase margin, or we may have to increase the phase boost. That means if we go back, I think we may have to increase this phase boost, because derivative will give some phase boost. So, let us again rerun this and let us check whether derivative provides some additional phase boost or not. So, now again we are plotting it and unity gain, and we are limiting to 0.6, 0.5, and we are making a phase adjustment. Yeah, and now we can get the phase characteristics. So, now we have enough phase margin. That means our derivative gain was smaller. So, we need to increase the derivative gain to get sufficient phase, and here also we got somewhat higher bandwidth. That means we got the bandwidth to be around 30 kilohertz compared to the earlier case, and the phase margin is now 50 degree. So, we have sufficient phase margin. Now, we want to see the transient response. So, if you see the transient response, so this is a low transient response of the boost converter. It is much better in the sense that we can get undershoot of around 140 millivolt, and then the settling time is coming to be around 0.08 millisecond. That means 80 microsecond, which means it is taking around 40 cycles, because it has a right up plane 0. So, the bandwidth is limited. And here if you see the inductor current waveform, this is the transient response. So, this response is pretty nice. So, you can design the controller very effectively. That means if you want to get additional phase, I would say you can increase this derivative gain. That means you can make the derivative gain somewhat higher. That means I can say for boost converter you can set 0.5 instead of 0.1, you can set 0.5. So, we will get additional phase boost, otherwise the phase margin will be very low. So, now we can convert all this into digital by means of this conversion. So, in summary, we have discussed, we have recapitulated frequency domain design of analog voltage mode control. We have discussed frequency domain design of digital voltage mode control in a buck converter. We have also discussed frequency domain design of digital voltage mode control in a boost converter, and we have considered some design case studies and MATLAB simulation. And I think this should be, this design approach should be motivating enough, so that you can design a voltage mode and digitally control buck and boost as well as the other converter. So, I have shown the approach. By this frequency domain approach, we can still maintain the same continuous time approach and adding the delay. But in the subsequent lecture, I will be showing this continuous time model is nice when you talk about the small signal based design, but as we want to push for large signal based design, then this model cannot predict different type of instability, subharmonic instability. Then we need to go for actual discrete time model, and that we will be taking in the subsequent lecture. That is it for today. Thank you very much.